Well, welcome back, everyone. Looks like it's time to get started. We're getting into week number 7, and with what we have going on for today so far, we should be getting through the 3.5 notes and potentially starting the next section notes on dealing with proofs, proof techniques. This will be our big application section to the logic we've been studying in section 3.5, and we'll do another proof section on inductive proofs as well in chapter 5. But any questions so far to get us started? Okay, and you probably have all seen the announcement that I wrote and sent out on Monday on the Canvas page. Sorry for the cancellation on Thursday's class. Glad you all made it today and didn't get confused on the day. I have a nephew who's in high school that's coming to the Idaho Falls campus to present a project in engineering. He made a robot dog and wrote some lines of codes to control it and those kinds of things. I felt I had to support him just because it's rare that I have a nephew on campus. So we're going to treat Thursday as kind of a catch-up day, that kind of thing. I'll try to get back in for office hours as soon as possible if you do have some questions. Aside from that, looking further on in the schedule, we're coming up to our second exam. It's going to be after midterms week. I didn't want to rush in and force a bunch of stuff on midterms week. That means when I get to Friday, one of the first things I'll be doing on Friday is getting caught up with the grading. And then I'm going to post the exact coverage for exam 2. Very next thing I'll post right after is going to be the formula sheet that will go on the last page of our second exam, and then a couple documents on sample exam questions. Pretty much the same pattern and organization that we did for exam 1. Well, any questions or comments at all then, folks, before we get started? Okay, well, let's jump back in. We're looking into quantifiers. So this is a topic that carries over from 3.4. They could have gone together, but it would have been kind of a big section. Altogether, this one's not too long, like section 3.4. And once we've made the jump with looking into quantifiers, nested quantifiers are really not too bad. For example, on our first problem that we took a look into, we were just looking into just a natural statement that we all know to be true. The sum of any two positive real numbers is positive. We quantified this by saying, because there's two numbers, any, we wrote for all x in a set of non-negative real numbers. Then we had to quantify a second number for all y in the set of non-negative real numbers. The sum, x plus y, is positive. So that was our statement. And if we negated it, we're really just carrying over the same exact rules that we used in the prior sections. The negation of a statement, whether it's quantified with nested quantifiers or not, is going to flip the quantifier statement from all to there exists when we negate. The set, or the domain of discourse, stays exactly the same. If this was an exist statement, we would have had a for all statement here, but we flip for all to an exists, and we do the negation of the predicate function on the right here. It was the sum is positive, so we wrote non-positive going this way. So that's the warm-up. We did an example 2 as well, but any questions so far, folks, with the refresher? Okay, in example 2, we're just going backwards. We have a fully quantified statement, and it looks very mysterious sometimes until we train our eyes to just read exactly what it's saying. It's saying for any real number whatsoever, that number goes here. Let me go for another shade. There will exist a particular other number n. That number n went here, such that the first number is smaller than the second number. We wrote this out for any real number that exists some other real number such that that number is larger than the first number. So here's our entire statement, just in ordinary words. Lots of different ways to phrase this, but as long as we are matching what the quantified statement is saying, matching the less than relationship here, then we've got a nice statement down. One thing that's really tricky, we should put down on paper right away, is the order of quantification sometimes matters. It doesn't matter if you have universal quantifiers nested. We could change the order, make x or y come first. It doesn't matter if we have existential quantifiers, we can change the order there. But if you have mixed quantifiers, the order absolutely does matter. And so we have to convey that order when we write it out as a statement. So here, the order of quantification, or I'll just say quantifiers, I think that's a better statement, matters. If we switch these quantifiers along with the variables that they're associated with, we come out with a different statement. And we know the statement to be true. Effectively, all it's saying is, if you pick any real number m whatsoever, we can find one that's larger. We just called it n. So now, just for the sake of practice, we'll negate that statement. And here's how the negation will work. We go from the universal to an existential quantifier. We'll say there exists an integer m. That's a real number. The colon we just read as a literal such that. Negate this, we'll say for all n and r, for any real number r, n whatsoever, we have this statement. When we negate, we also have to negate the predicate as well. And the tricks of this are, if it was a less than, we now include equality and we flip it to a greater than at the same time. So we'll write m greater than or equal to n. And that's a weird statement if you look at it. The first statement was absolutely true. In the real number system, there is no maximum upper bound whatsoever. But this statement is saying we have found one real number so that it doesn't matter which number you find. For every real number n is less than or equal to it. That's impossible. You can't put infinity here because infinity is not a real number. It's just a concept and a symbol. So this statement becomes absolutely false. It's asserting we have a upper bound on the real number system, which we absolutely do not. Well, that's our warm-up so far with nested quantifiers. Any questions or comments getting through either two of these? Okay, so these statements, they really weren't too bad, just ordinary kind of compactly written mathematical facts, both on example 1, example 2. But sometimes these things do get a little messy, especially if we're looking into technical definitions like these. The definition of a function has quite a lot going on with it. Definition for onto has a lot going on with it, and so does one-to-one. I'd saved the one-to-one example for the homework problem, so you can see the notes here to see how these go. And it's kind of amazing in a certain sense that this is a definition that we've learned from early days in algebra, the definition of a function. It's essentially saying that your function has to pass a vertical line test for thinking geometrically. But if you want to quantify this statement, there's a good amount of work to do on this. So let's work through this carefully, see how it'll go. I want to give two different kinds of solutions, and they're both going to be acceptable. So I'll put up here solution 1. This is going to be the fast expression. I'll just say fast answer. And down below, solution 2. This one is a little bit more messy, but let's call this the precise answer. They're both going to be fairly precise, but you'll see what I mean when we get into this. One of the things that's really tricky about this definition is this one word right here. If you want to capture the definition of a function, you have to include that. There's a unique output b to every single possible input value a. We write in function notation f maps a to b, but we have a unique value right here for b. Okay, this gets us started. So let's say f mapping from the set A to the set B is a function. Oh, hang on, that was supposed to be an eraser. Is a function means the following. Let's read through the definition again. It says f mapping A to B assigns to each value A in A. When they say to each, that's just a different way to say for every or for all A in A, we're going to assign an output value. So it's right here, assigns to each input value A and A, because this is saying essentially for all, for every, or to each. There's lots of ways to say it. We begin with a universal quantifier. And let me make sure my colors go in the right order. I want to go green for domain, blue for codomain. So I'll begin by saying for all, A in the domain set A, it's going to assign a unique output value, B, in the codomain, B. So here's where this becomes kind of a fast answer. When it says a unique output, we're just saying there exists a number. But there's a way to say with an existential quantifier, uniqueness, a unique B in the set B, the codomain. The way we can express that with quantifiers, even though our author didn't discuss it, I would say this is a fair game symbol. It's something you've possibly come across. It would look like that. If you put an exclamation mark there, we're saying there exists B and it's unique at the same exact time. So it's a brand new symbol. Let's put here just to define it, means there exists a unique element, and then we would pair that with a domain. Have folks seen this symbol before in other contexts?
In programming, it can be used for a not operator.
Oh, gotcha, yeah. So here, combining with existential, we're just saying exists unique. That's what makes this one kind of fast, because we captured some of the trickiest part by just using one specific quantifier. So if we didn't use this, what's kind of a hack at this point in a certain sense, we'd be giving the precise answer, and that's what we'll do below to see what it would look like. But so far we're saying f mapping A to B is a function if for every element in the domain, there exists an element in the codomain such that we can just write something went wrong here. Let me fix that. F of A equals B. To borrow the function notation, F is mapping A to B. And that B value is unique. Another thing you could do here if you didn't like that symbol, because it is a brand new symbol just kind of chucked at us, you could have went like this. F of A equals B, and B is unique. I would say that's okay as well if you're doing this kind of problem in this context. Again, it doesn't seem like it's completely capturing the spirit of the question, redefining the definition using quantifiers. If I just state that in words, I didn't actually really quantify uniqueness. So I would say that this is a better solution. It is a standard operator for quantifiers, exists unique. And so it captures the uniqueness up here that we were looking into. Well, does that make sense to folks on quantifying the definition of a function so far? Okay, and let's suppose we didn't use any tricks like exists unique quantifier right here. We're not going to say and B is unique. We want to really quantify it. Here's what the whole definition would look like. Assigned to each input value A, so we're saying for every value in the domain, for all A in A, we're going to assign a unique output value in the codomain. We'll say here such that there exists B in the codomain, uppercase B, such that F maps A to B. We still need that statement there, so I'll write F of A equals B. But we have to put this into parentheses because it's going to be a compound statement. So I want to say this condition, and at the same time, here's where we're going to capture uniqueness. We want a big compound statement. If we're describing uniqueness, we're talking about uniqueness on this element B right here. We need another quantifier. So we're going to begin by saying, and for every element, let's say we can't use B again because we're describing uniqueness. We need to describe a different element coming out of the codomain. I'll say just the next letter in the alphabet. For every for every element C inside the codomain B, such that F maps A to C. If this happens, this will imply right away that B must be equal to C. So this is the essence here of uniqueness. What we're saying is check every other value in the codomain. If you have a match here, the only way that could ever occur for uniqueness is the function output B and the function output C here must be the same exact codomain element in the first place. So that gives us what we mean by uniqueness. It threw a quantifier inside an already quantified statement, but that's fair game for these kinds of expressions. They get pretty large and messy. That's why this is a nice, slick way to say it without having to blow up a larger, bigger statement like this one. We've got it, folks. We have now the definition of the function from chapter 2, now as two different versions of a quantified statement. Any questions at all, folks, getting through this one? Okay, the function definition is pretty tricky in my opinion. There's lots going on here. Capturing the uniqueness is the harder part about it. But the other definitions, they're really not as rough. On2 is pretty decent. One-to-one is not too bad either. And so we're going to quantify for the lecture notes what On2 is going to look like, and then leave the one-to-one for the homework exercise. So here's the definition from before. On2 just essentially is saying that every element in the codomain is hit by some domain element A. We have full coverage of the codomain space B. So we'll say a function mapping from A to B is onto. The statement that we wrote is, for every B, notice we're starting with the codomain first. For every B in the set B, there exists at least one A in the set A, for which F maps A to B. An onto function is called surjective. I don't know why I read that out. We knew that, but here's the essence of the definition again. Now, one thing we have to be very, very careful with in all of these, let me just pull this up so we can see these side by side, is the order of quantification again absolutely matters. For defining a function, the for all begins on the domain. Oh, hang on, I should probably keep these colors the same. Let me not swap those around. We're going to go green on this, blue on this one. And then for every B and B should be blue. Sorry for the bad color coding there. It's supposed to help, but if you flip it while comparing, this is going to hurt our comprehension on this, at least for me. So for the function definition, we had to start with the domain, then do an existential quantifier on the codomain. But this one goes different. The way the statement is said verbally is indicating an order in the quantification, and we have to maintain that order when we quantify the onto statement as well. So because the statement begins with, for every B in the codomain B, we need to start off by maintaining that order of quantification and write for all B in B to start. So for every codomain element, we have to pair it with at least one domain element. And this doesn't have to be unique. If it is unique, we're looking into a one-to-one function. But here, it's an ordinary existential quantifier when we say at least, or there exists at least one element. So we'll begin for this part by saying there exists an element A in the domain set A such that, then all we have to say now is F maps A to B. F at A equals B. Again, this one's kind of tricky because if we were thinking about how we define functions, we might have accidentally started with the existential quantifier first. Kind of makes sense. The domain comes first when we say F maps from A to B, or F is a function from A going into B. But when we're discussing onto, that statement has to come first. Well, any questions at all, folks? Quantifying onto? Okay, in terms of quantifiers, this is the essence of what we mean by onto. What we're going to do next is negate the statement in part A. And if we negate it, we have a nice quantified statement for what it would mean for a function to be not onto. So here, this is now an onto function, or surjective if you prefer. Negating it is giving us a nice quantified statement for not onto. But as far as negating statements go, it's kind of business as normal. We go left to right, maintain the order, flip the quantifiers, negate the predicate function, which would be this statement, F maps A to B. So we'll go, there exists an element B in the codomain such that for every element A in the domain, F at A is not equal to B. So we did negation by flipping quantifiers, putting a not equals where we had an equality before. And now this is saying it's not onto because you found at least one. There exists a codomain element such that on every domain element you checked, every single possible one, you never got equality here. This is what not onto would mean as a quantified statement. Well, we did, folks. That's looking at function definitions and properties. Now, through the lens of quantifiers is kind of an interesting point of view to take. Any questions at all with this kind of practice?
So with this, we're just making statements, not true, proving whether or not they're true, right?
Yeah, exactly. So we're just saying, what does it mean for onto? What does it mean to negate? But we don't have any particular function where we're proving onto or not onto, like on the exercises. Other questions at the moment? Okay, well, we're nearly done with a section 3.5, but there's still a couple more topics we want to get through. One topic is look at like just doing another translation. We're going to write down the statement using quantifiers, then a related statement at the same time. That'll round out example 5, kind of similar to what we've done before, except now we have nested quantifiers in the section 3.5. Then we'll end the section doing it again with another predicate function using quantifiers. But the big takeaway with this section is we're going to look into the topic that we briefly, very, very briefly discussed in chapter 2 on writing out pseudocode. So this will be, again, another kind of interesting take going from a quantified statement into nested for loops, writing pseudocode is the major challenge of the notes. So this one will be like a warm-up getting there. We have a predicate, P of xy. This is going to be defined in these terms. P of xy means person X is a parent of person Y. And notice the order of inputs into this predicate function is very, very crucial. If we swap this around and go yx, then we're saying person Y is a parent of person X, changing the order here. Whether we call them X or Y's is irrelevant. What is very relevant is the order the inputs, the arguments to the function appear. We could use A's and B's or keep it X and Y's, but always regard the order, reading this left to right. we'll say, it says, write the logical statement using quantifiers and standard logical connectives and the predicate function p of xy. So lots of requirements on this one. To denote each of the following. Every person has a parent. There's a person who's a parent of everyone. One thing that's missing before we even get started is, what is the domain of discourse? That's the very first thing we want to put down before we try to quantify any one of these statements. So let's begin right there. Let's start by saying U is going to be the set of all people, because the relationship is person X is a parent of person Y. We mean alive or dead. So living or deceased, however you'd like to say it. I'll go with alive or dead. It's faster to say. So all people alive or dead is our universe U. Now that we have the actual domain of discourse, we can look into this predicate function a little bit closer. Recall it's a Boolean valued function. It's an ordinary function like the ones that we just quantified on the prior examples. So this is a function P. Now it's going to map from U cross U. Or if you prefer, you can say U cross U is U squared, or much like R squared, the plane, or R cubed ordinary 3D space. So we're going from U cross U into true or false. So that's the Boolean valued aspect of it. So that's our predicate function. We now have a bona fide domain of discourse, and so now we can write a pretty precise statement. It says every person has a parent, and that sounds like a true statement. We can begin by writing for all. That makes sense because we're starting with every person, but we have to be really careful at how we put this together. The first one I'm putting down, I'm going to think of as, let's say, an A in U, or you can keep these X's as X's and Y's. That's really up to you. Then for the next one, I'll say for all B in U, because they're both universal quantifiers, I can swap the order. That's okay. But when I go to write out the predicate statement, we have to be mindful of exactly what will go inside this function. But let me think about these quantifiers very carefully. Every person has a parent. I started with a for all, and I put a for all here, but I'm debating myself. I feel like one of these ought to be an existential one. Let me say for the every person, this part right here, let's color code this just to see the relationships. I'll think of this one as being the statement in blue. I want to say every person for every person. There exists a parent is another way to phrase this, right? So I feel like putting it for all here was possibly an error. Let's go with exists. There exists a parent. So exists another person, either alive or dead, in the set U. But now that we've done that, we have to be very mindful. What goes in the first position? What goes in the second position? It says person X is a parent of person Y. So if I put A here, I'm going to say this person, every person potentially, is a parent of what goes here, B. Let's take a really careful look at that. Would you all say that's the essence of the original statement, or did we mess it up if we go A and B? Yeah, I agree with that. Here we're saying everybody is a parent because it was a universal statement here. Everybody is a parent of the person in the second slot, person B. But that's kind of weird. That doesn't seem to be capturing what this is saying. We're just saying to every person out there, we can say that there is some other person who's a parent. So let's swap this around and take a look at it. B and A. Now, if we go in this order, we're saying for every person A, there exists a person B such that, putting B here, person B is a parent of person A. Maybe X and Y's might have been a good way to really see the correspondence instead of kind of doing the translation between these values. But this looks like this is the essence of what we were trying to say. We're now saying for every possible person, there exists a parent of that original person. So let's go in that order and keep it as B, A. Again, that's pretty tricky. We have to maintain the relationship that the predicate function is trying to denote. Let me undo that highlighting there because we have different meanings for the highlighting. And think about what the quantifiers are. They weren't really stated very nicely. I think if this was a good exam question, I probably would have rephrased every person. For every person, there exists a parent, something more explicit in that kind of way. But with ordinary English language, this is possibly how most people would phrase the statement. And this is their intent, that quantified statement there. Any questions or comments at all, folks, writing it out this way?
I don't get the statement 100%. Could you explain it again?
Yeah, absolutely. So are you referring to mainly the predicate function right here for the statement?
The whole thing. I like understand it, but I want to have the whole like connection.
Yeah, I gotcha. And that's really tricky because the order here is really critical, and we're making a whole bunch of jumps, right? We're jumping between a universal, an existential, a domain of discourse, all people, and a predicate function at the same time we have to translate through. So when we look into this part, P of BA, this is saying maintain the order of the inputs. We put a B here and an A here. So B and A, we're saying person B is a parent of person A. So that's then B and A in the statement. Then we would look in the quantified section portion right here. This is saying for every person, so we start with that. Next, we have exists another person B in the set U. The B was special because it went into the first input. It's implied that that person is not just an ordinary person, it's a parent, also a parent of person A at the same time. So we'll say here, there exists a parent. Then the colons will just read as such that person B is a parent of person A. So for the every person, we have the universal, and we can think of it in these terms if we unpack it. Has a parent just means there exists some parent of that person. So that's the quantifier, and this part is unpacking it. And then the predicate function, finally, putting it all together, is saying for every person, there exists a parent of that original person. Does that help seeing it in those terms?
Yes, it does. Thank you.
You bet. And yeah, this is really kind of tricky. I think person X and person Y is doubly tricky in the sense that the domain of discourse is U for both of them. There's different ways we could have wrote this out. We may have said U is all living people, right? A different domain of discourse, maybe capital P, to be all parents, alive or dead. But with just one domain of discourse, mapping this way, this is a valid solution as well. Now we have a different statement to quantify, but other questions first? Okay, this one is kind of a weird statement. There's a person who is a parent of everyone. Definitely a false statement, right? So we know that to be false, but we're still going to quantify it, put it down on paper, what that false statement would look like quantified. So there is a person or there exists a person is how we're going to start for this part right here. Kind of debating on the color coding there. Let's leave the color coding off for the moment and then flag it as we're checking it. But when it says there is a person, that's definitely an existential quantifier. So I'll say there exists a person who is a parent. I'll use B because we're thinking of B being the one that's a parent. It could be A, that's okay, as long as you put it inside the predicate function in the right order. It doesn't matter if you call this A, B, X, Y, U, V, and so on. We just have to be mindful of the function mapping itself. So I'll try to keep this consistent by saying there exists a person B in the set U, all people alive or dead, such that that person is a parent of everyone. Being a parent of everyone means we now have to use a universal quantifier. This is going to be a for all situation. So instead, there is a person. That's the existential part. It's going to be a parent for everyone. So we'll say for all. Everyone here gave us the universal quantifier. And I'll say for all A in the set U once again. Then this is a good point to pause and reflect what should go in each portion. There exists a person who is a parent. So I'm thinking of this one being the person, being the X that goes inside here. The first input is the parent. So I'll put this B into the first position, following the color coding that we see above, such that this person is a parent of everyone. When it says of everyone, we mean all people alive or dead. So that's the A part right here. So being a parent of person Y, that's the part that goes in blue. That's the second input, the second argument to the function. So A would go here as well. So this is now saying there exists some person, either alive or dead, who is a parent of every possible person. If we write out this statement, person B is a parent of person A, but A is quantified as a universal quantifier, so we mean all possible people. So that's our statement. Any questions at all with writing down part B? Okay, it's a pretty bizarre statement that we wrote down. And notice the statement in part A, the statement in part B are absolutely different statements. 100%, they don't convey the same information. Every person has a parent is not the same thing as saying someone is a parent of everyone, alive or dead. They mean totally different concepts. But the big takeaway here, the reason we're doing this kind of problem is, notice it's almost the same statement, almost chillingly so. The only difference between the quantified statement in part A versus the quantified statement in part B is the order of quantification. And so the big takeaway here is, for mixed quantifiers, the order of quantification is crucial. What we mean by mixed quantifiers is an existential with, or excuse me, a universal with an existential or vice versa. We don't mean a for all against a for all, or there exists against an exists. We mean mixed in these two cases. Well, we got through it, folks. These problems are always kind of challenging, especially when there's a complicated predicate function coming from a domain like U cross U or U squared, however we say it, because now the relationship of how the inputs work is the big factor of this as well. We'll take a look into this on the application problem below, and really just extra practice with the same kind of concept. But also the big takeaway with this one is practicing pseudocode once again. We'll do even more pseudocode when we're in chapter 5 looking into proof by induction, and quite a lot of it when we're in chapter 7, when we're looking into number theory and the algorithms around number theory. But here's the context on example 6. This one's a pretty realistic application, more than it seems, even though it looks like a kind of a simple situation. It starts off by saying, just suppose for the moment, you are a high-level technical administrator for ISU working for the registrar's office. So you have access to lots of pretty interesting, humongous databases. And we're looking into 2 different kinds of databases in particular. We're going to define the set S to be the set of all students at ISU. We can take that to mean, even though it's not precisely stated, we're probably taking that to mean all current students and possibly also all past students of ISU. The registrar needs to keep track of everyone at the same time, whether they're current or former students. We're going to define the set C, or as our next database, to be the set of all courses offered at ISU. Well, this one's kind of a tricky one to think about too. It's not written precisely, but in the context of the registrar's office, they need to keep track of all courses that are currently offered, as well as courses that have been offered in the past and are no longer offered. They still have to keep track of it. So if something was offered in, say, like 1950, something like that, but that class is never offered, that class is probably still in this database C. So these are our largest possible type databases. We're going to define the predicate T. TXY means student X has taken course Y. I notice fundamentally it's not different at all from the last problem we're looking into, other than there's 2 different domains that we're looking into, S and C. So our predicate function says student X has taken, that's why we're calling it uppercase T, T for taken, course Y. And as a true function, like the one that we quantified above several examples ago, it's mapping from S cross C into the Boolean values. T, if they have student X has taken course Y, false other words. So that's our statement altogether. Any questions at all, folks? Just deconstructing the context and the function. Okay, so we're going to look into the statement. Every student has taken at least one course. And just for the sake of not making this problem too long, it's not completely precise what we mean by has taken, but I think this, when I was writing this problem, I was thinking this to mean, when we say has taken, let's think of this as the course is completed and a letter grade assigned, which is a whole different function mapping, assigning the letter grade to the student relative to a course. But that's what I'm thinking about when I say has taken. The past tense, we're saying the course is over, a grade is assigned. And we're looking into the statement, every student has taken at least one course. That's probably false, right? Because there is assuredly freshmen who are in their very first semester here at ISU, and they haven't finished a course yet. So we expect this to be a false statement. Nonetheless, we're going to write it out as a quantified statement using the Boolean function T as well. So starting this off, when it says every student, that's the universal quantifier. We're saying for every possible student in the set S, compactly, it would be for all, I'll stick with X's and Y's on this one. X in the set S, we also have to say there exists a course that this student has taken. So we use the existential quantifier when we see at least one or there exists, or if we see for some, anything along those lines. So there exists Y in the set of all courses, uppercase C, such that That student has taken course Y. So we'll just write out T XY, maintaining the firm order of inputs for that predicate function. So we've got it down on paper. There's a predicate function. And thinking about this one a little bit more, I think this one is easier than example 5 to get through part A, only because it's very specific which set you're using and then which input goes along with that set. In the prior example, we reused the set to U and had U cross U. I think that makes it a lot more tricky to put it down together here as a quantified statement. Well, any questions at all, folks, with the quantification portion? Okay, now what we want to do next is make another leap on this. We want to take a statement like this, which is really just pure logic, no major logical connectives. We don't have and, or, implies, and so on. But we have quantifiers. We want to rewrite this in terms of pseudocode. Again, we did this once, but it's been a while, quite a while actually. What we mean by pseudocode is just a algorithm set of instructions that you could adapt to any convenient programming language you happen to be working in, whether it's Python, R, Java, C++, and so on. When we did this in section 2.2, we were just introducing the concept of pseudocode by demonstrating we could take a for loop, a summation symbol like this, and re-express it as a for loop. And it's kind of curious, if you take something that feels familiar, summation of 2y, just repeated addition where you're changing the index, writing it down as a mathematical expression, expanded, feels a lot different than writing down the pseudocode that would represent that operation. So for the summation, I goes from 0 to 5. We start by saying for 0 to 5 on the index I, but we had to initialize a sum to start this. So we said sum gets itself plus I minus 1, where the value of I came from this set. Then we just loop through this, output the sum. And on the right, we verified it made sense by just tracing through the whole entire statement to make sure we got the sum 9 that was expected. So again, this is really basic code, right? If you're working in other programming languages, when you initialize this, you probably have to say what the data type is. The for loop might look quite a lot different. So this is some really pared down syntax. It's pseudocode because it's highly, highly adaptable. We're just thinking about the logical process of how you might implement this in any coding programming language. So now we're going to do the same for the universal quantifier. But any questions with the refresher, what we mean by pseudocode in the first place? Okay, let's give this a try. First, to kind of motivate what we're even doing here, this seems like just kind of a weird curiosity problem, but it's actually very, very highly applicable in the real world, more so than we might think. Because a high-level technical administrator for ISU has a lot of tools, really, a whole dashboard, a suite of operations. They can just punch something in and do a check. They can punch the statement in and it's going to tell them yes, no, true or false, and they're done. But things happen, things break. Sometimes we're migrating data from one platform to another, say like Moodle to Canvas, or something could just go internally wrong with the databases. And when things break, we sometimes have to audit the systems, write out pseudocode like this to see where the logical failure occurred as we're diagnosing the system. So this kind of stuff is pretty realistic in reality. Even if you are at the highest level administrator for ISU, this is stuff they probably did from the Canvas Moodle to Canvas migration, things along these lines. So to get started, writing down the pseudocode from scratch, not using any of the fancy tools that they would have access to, we need to begin a loop starting with this. It's going to be nested loops, which coincides with nested quantifiers. So that's kind of a nice correspondence there. We're trying to see if this statement comes out as true. And if it does come out as true, there's probably something wrong with our system, something wrong in the databases, because there's no way that every single student has taken at least one course. Surely there are freshmen taking their very, very first classes at ISU. They don't have a letter grade assigned. So we're going to test this out in our system to see if it's behaving as normal. Starting here, let's write out for, again, it's pseudocode, so I'm not trying to write out anything fancy in any one particular language. I'll just say, like we did with the summation symbol, for X in S. So that gets us started. That means we're going to check for every value or every possible student through this loop. I'll put a curly brace here just to organize the nested loop structure. And I need a Boolean value to start with. We're eventually going to use a predicate function inside of our pseudocode, but I need a placeholder, much like I needed to start an initial sum right here, starting at 0. So I'm going to begin by just saying something along the lines of taken course, something kind of basic and fast. I want to initialize this as a Boolean false. And if we flip this to true, we just want to stop that code, return the whole statement true, to say we found that for all X and S, there exists Y and C, such that student X has taken course Y is true. But here's where we're going to start. Taking course, initialized false. We have a student. Now we need to check every single course against that one student. So we begin another for loop. Keeping the indentation, I'll go for Y in C, another curly brace, and we need to do a check. It's going to be a check on every single course, Y in a set of all courses. Here, let's see, does that come out as true? If it does, we need to do something, because this is a statement saying for all X in S, there is some course. Every student has taken some course. If that comes out as true, we can just stop on the first course where that occurred. So I'm going to write for Y and C, if T input X, then Y. We're doing a comparison operation, so we'll say is equivalent to a Boolean value of true. Well, then we need to do something. We have found that we're done. We have a true statement altogether on this one. We can set this one to a Boolean value of true altogether. So let me say if T of XY equals true, it's a if-then statement. I'll write it as a basic curly brace here to start the output. Then set taken course. This time we're just going to give it a new value, overwrite the false with a true, and we're done with the for loop. We don't have to keep checking every single course any longer. We could if we want, but we might as well stop, save some compute power, and just break out of the loop. So after breaking out of the for loop, I'm really done with the if statement, so I'm going to close the if statement here. We're done with this for loop, so I want to close this original for loop right here. But we're not done with the outer statement. There's still more we have to do. So let's suppose this if never ran, then taking course is going to be false for that one student. It'll stay false. Then we'll go to the next student, run through, and it's possible the if block never ever runs again because the next student potentially never flips to true. In that case, we need to write down something here to say what the result should be. Anyone see what should come out next at this stage? Sorry, say again. The break right here. It is very confusing, yeah. And for full disclosure, I have a cheat sheet right here in case I lose my way, because this is a weird way to think in a real sense. Let's kind of recapture what we're trying to say. We're trying to say every student has taken at least one course. We think it's false. So if it's false, we want to output that. So if we start with one student and we find a course, or excuse me, we put taken course equals false here, then loop through all the possible courses. The moment we get a true, we're just going to break out of there and search for another way we're going to get false. So keep looping through all the students' X's, looking if we can ever possibly flip to true. And if we can't, we can write down this statement. If taken course is, let's make a comparison check, false, still false altogether, we're going to return false. We're just going to end and say we have a false on this. Altogether, the syntax will end. This would end the for loop right here at this stage. And then we would go to return true at the end input. If we never get here, then we'll return true to say, yes, in fact, every single possible student X has taken at least some course, at least one. Student X has taken course Y. We've flipped this to true somewhere. The predicate was involved here, but let's still pause on this one and think through it. There's a lot of weird choices I had to make, right? One weird choice is, why did I put that specifically right there? Could we have put it at the top? We made a very delicate consideration putting it in that location. If we put taken course, say, equals false at the very top, this would have become an overall just global statement. But we want to reset the memory on the taken course Boolean value for every possible student, not just as an overall statement here that we never check again. So we didn't put it at the very top because we're trying to see, is this going to come out as false on every single student? And we initialize it false to start on one particular student. Then we loop through every possible course offering at ISU, present or past, and see if, will we ever get a true statement out? We get one true course for that one student, we're done. We're going to break out of this right here. Taken course is going to be set to true. Break out of the for loop. We have a true in this case when we break out of the for loop. We're assuming that one student has, X has taken that course. Break out of this loop. Go back to X and start over. So this is now student number 2 we're looking into. We reset the entire Boolean because we're doing a search on every student. We need to reset this one every single possible time. If on student number 2, we go through here and we manage to flip that to a true again, well, we stop searching, we come back to the top and look at to student 3, reset the Boolean, and if we keep on getting true, notice what will happen. Suppose we hit true on every single student in the outer loop X in S. Then this block will never ever run. And it would have been helpful if I put a curly braces on these. Let me just slap it real fast with some, just to say where the if block will be, where the scope is. So if we run through here and we got true, flipped on every single combination of student, and now we're done with the last student, done with the loop Y, this never runs because we have flipped it to true. We're done with the last student. It'll never flip back to false. So we skip this block and we return true altogether. We're now saying, yeah, after we looped through our database, the way it's structured right now, on every student, there exists a course Y that made the predicate function t of xy true. So we flipped to true on every possible student. So we never run this and we return true. That is saying that this would say it's true for our databases. Every student is flagged as taking at least one course. Now we know there's a major logical problem because it's, again, probably not a true statement for the real database at ISU. But let's imagine this if block never runs. Another take on this. We're asking the question again, just starting over fresh, thinking about the logic and the structure. Is it true that for every student S at ISU, there is some course Y in the catalog of all courses present and past, such that student X has taken student Y? Let's see what would happen if we did hit this block. What would that look like? We'll start with the student X, initialize false. Now we check against every possible courses in the set C, courses Y, and let's imagine this if block never executes because the predicate function is false on that very first student. That student hasn't taken this course. So if we get to false here, if block doesn't run, and then we leave. But if we never flagged a true, we found one student that hasn't taken a particular course Y, and we're done with that one student, we don't loop to the next student. The if block right here will execute because taken course is still false. We make that comparison check that executes as true, and then we're not looping anymore. We're going to stop all loops. We're done with the outer one. We're down with the inner one. We're just going to return a false statement. This would then mean we have in fact found one student for which, for every possible course Y in the catalog of all courses C, this never came out as a true statement. So that's why we return false right at that level right there. And again, that's just another pass through here on the two possibilities for this syntax. In my opinion, this is really tricky. Again, I practiced this like 4 or 5 times, trying to convince myself of the logic, and I have a cheat sheet here that I was kind of peeking at. I don't know if you've noticed, but any questions about how this came together so far? Okay, at its heart, it's really just doing this. It's nested loops with quantifiers, but we weren't doing anything that fundamentally different. The reason it got more complex was there's an extra predicate function in the middle. Really, when we're thinking about quantifiers, the big thing that's always there, always in the background or in the foreground, like if we indicate the function notation, we're making a big deal out of it, it's the predicate function. So that's always the big takeaway. We can't fully understand quantifiers unless we have a good handle on how does a predicate function itself work. And the other takeaway is, even though this is a pretty challenging problem, we'll have opportunity to practice it, but we're going to be looking into a lot of different kind of algorithms as it relates to number theory. We're going to look into Euclidean algorithms, a mod and div algorithm, see how it comes together with different concepts, interesting concepts of number theory. So this is just our first, well, really our second big look at what is pseudocode, how do we go from logic to something practical. We're going to try to run our pseudocode. We ran this one when we were in chapter 2, and when we're in chapter 7, we'll be running pseudocode as well. That's not something that's always required in this course, but it's always good to demonstrate, is the code correct, by actually attempting to run it. This question's harder because I can't run it unless I come up with 2 different databases. And so this one is more just about running down the nested quantifiers. Well, it's a pretty challenging problem. You'll have an opportunity to practice this one in the homework. And if you have any questions about it, don't hesitate to ask. I'll be very happy to help out. Any last questions at all, folks, before we turn over to chapter 4? Okay, well, let's take a look into chapter 4, our first big application of essentially everything we've done in chapter 3. An application of logic is essentially proofs and proof techniques. I did want to load up one diagram before we get too far in these notes. And that's going to be all the way in section 3.2. Propositional logic, we're going to take another look into. And the table I'm most interested in is, as always, the implication. This one just has an interesting way of being very relevant to a lot of different problems we're looking into. In a certain sense, you could say a vast majority of mathematics is just a huge house of cards with stacked implications going on forever, essentially. But here's how the notes start. For just a fast definition of what we mean by a proof, we're talking about a proposition statement, so much like the propositions in 4.3. And the proof of a proposition is going to be a convincing argument that the proposition is true. That's not the world's best definition you can imagine, because now you have to qualify what do you even mean by a convincing argument. A proof is really nothing but just a bit of writing. And so a convincing argument depends on what the audience is. The audience isn't really me. Even though I'm going to be grading it, I'm going to definitely be reading your proof arguments. The proof that you're going to write is going to be written for the audience of all students in this class, our class. So what I mean by that is when you go to write your proof, you need to quantify things. You can't throw down a variable without saying exactly what the domain of discourse is for that variable. You have to show all the logical algebraic steps, the steps that you would expect your fellow student would understand if you wrote this down. And you also have to say what the conclusion is so that I know that you have ended at the right step and made it the correct conclusion we had to show in the first place. We'll be doing all these really carefully in the notes. The homework exercise, I wrote custom problems to go along with the ones we see here. And so you can use these notes here as a structure to help out the homework assignments. We'll be harping on each one of these 3 bullet points quite a bit on just about every problem. And when it says we're looking into proofs and proof techniques, the first major proof technique we're looking into is the direct proof. It says the direct proof of a proposition starts from known facts, whatever they might happen to be, and implications, repeatedly applies logical deduction to derive new facts, eventually leading to a conclusion phi. So if we take that whole thought of what a direct proof is, and look into this implication table, this is really what it's all about. A direct proof is proving these kinds of statements. We start with known facts, whatever they might be. That's going to be the P side of the proof. Known facts and implications repeatedly apply logical deductions and derivations to derive new facts. That's the steps in the middle. So there's probably lots of implications in the middle that we have to work through. We want to eventually lead to the conclusion phi. That's referring to Q. So we're going to start off by doing this type of proof. We're going to have a statement, if some proposition P, then the implication, some other proposition Q. So this is the P and the Q in the statement we're looking at below. As far as the structure goes, really, we don't have to worry too much about a lot of rows here. We don't have to worry about proving P implies Q with vacuous truths. Well, in other words, we don't have to worry about negating n is odd. We don't have to consider at any point in the direct proof of this, n is even. Because if n is even, that's putting a false here. We get vacuous truth on the implication that we're looking at down below. So we skip those 2 rows. That's no issue for us. We start here. We assume that the initial proposition P, whatever it happens to be, ours is n is odd, is true. We're going to just say straight out, n is odd. Make that our assumption, our whole reality. Then our hope is we conclude Q comes out as true, If we can make that happen, that's our proof. If we've got false, there's a problem now. If we come out with false, probably the statement was just wrong. I'll try to never do that to you on a homework setting or exam setting. We're expecting true. If you're told we're going to prove the statement, then we assume the statement is true from the very beginning. But if it was just a random statement in the wild, and the question was prove or disprove, that would be a different course. We'd be considering either one of those possibilities to determine if we get a true or false for that statement. True would mean we proved it, false would mean we disproved it. So that's the structure of the direct proof. When it says we have to start from known facts, here's our known facts. We previewed this when we were in section 3.3. If n is even, all that means is there exists an integer k such that n is double k. And if n is odd, there exists an integer k such that n is twice k. That's even, but then add 1 and you automatically flipped it to an odd number. Using these two basic tools right here, we can prove some interesting statements. If n is odd, then n squared is odd. These aren't going to be the most earth-shattering proofs that we're going to prove on these notes, but they are pretty interesting in their own right. The reason I'm not going to ask you to prove humongous statements or big facts is we're just trying to emphasize the proof techniques. And we don't want a humongous statement, some like fundamental theorem of calculus statement, for example, to kind of overshadow the major objective, the proof techniques. So we'll start with the direct proof. Next one we'll look into is going to be proof by cases. So we say for every integer n, cases are, well, n could be odd or even. And we're saying n squared plus n is even regardless. So we have to break this up by cases, give two direct proofs. We'll next look into proof by contrapositive. So this is one we made a big deal out of in the section 3.3 notes, I believe, with a particular logical equivalence. We'll prove a biconditional statement, the if and only if. Finally, we'll look into proof by contradiction. This is one of my favorite ones. We can prove things like root 2 is irrational. And we'll look into counterexamples, disproving a quantified statement. So that's going to be the landscape of the notes. But really, it's all going to start here. We're just taking a look at the implication once again, working through the direct proof. Well, I'm kind of short on time to really get through this one. I just wanted to kind of introduce what this is going to be all about when we return next week on Tuesday. But any questions or comments at all, folks, before we call it a day today? Okay, well, when we come back on Tuesday of next week, we'll get through the proof techniques. Chapter 5, we're going to look into proof by induction, which is a great method that comes up with lots of formulas that are essentially recurrence relations. We'll look into pseudocode as well. So we'll be able to write down something in pseudocode, use our proof techniques, and actually prove the statement is true mathematically, and then run the pseudocode as well to demonstrate it behaves as the way we think it is. So essentially, chapters 4, 5 are just going to be big applications to everything we've done in logic so far. But have a great weekend, folks. Just a reminder that I have a class cancellation on Thursday's class, so we'll be back on next Tuesday. But have a great one, folks. If you have any questions, don't hesitate to reach out. I'll be happy to help. Awesome, thanks. See you later.